Hello, my name is Nicholas Nunu. I'm a senior in the engineering honors program at the University of Michigan studying biomedical engineering. Today I'll be presenting to you my honors capstone on the roll-to-roll microfluidic artificial lung. This is a project that I've been working on for the last 3 years through the VA hospital in Ann Arbor under Dr. Joseph Patke. Some logistics. To present to you my poster, I'll be zooming in and out of different parts of the poster as I go and talk about them. So firstly, into our introduction. The reasoning behind this whole project is because chronic lung disease is a wide sweeping disease across America, with 24 million people suffering to it, as well as over 150 deaths each year. There are current treatments for for chronic lung disease, including artificial lungs, often also go by ECMO, the acronym ECMO. And while these work for currently, they could be greatly improved and have more capability in helping patients. Specifically, one drawback to these is that for them to function, they require a high amount of anticoagulant or anti-blood clotting serum to be given to the patient, which is not good because this inhibits the patient's ability to blood clot when they do need it, along with when they don't. So we hope to create a device that can start to minimize these negative effects. And that's where we come to the work of our research lab, which is microfluidic artificial lungs. And this takes the study of microfluidics, which has to do with very small scale volumes, or very small scales of volumes of fluids. And we incorporate these ideas into our artificial lung. The reason we choose to do this is to mimic as much as possible the natural lung environment that the blood would be in when being oxygenated. So when passing through a normal lung, the blood is actually narrowed down to very, very small vessels, even to the size of a single blood cell passing through. So we accomplish this also with our microchannels. Still, though, our device, while very good at oxygenating blood and mimicking the environment of the lung, it is smaller than what is needed to be able to be effective in the human body. And this happens because of the manufacturability of the device. And that's where I come in with this project, working on specifically roll-to-roll microfluidic artificial lungs, which is a new manufacturing method. So moving on, and I'll explain what roll-to-roll means in a second. So how our device works is we engrave a pattern of blood channels and gas channels to allow for blood and gas exchange in our device. And this pattern is printed, laser printed onto a PDMS film that is about 100 microns thick. So it's a very thin film. The film is then rolled up onto a PDMS tubing substrate, and it's rolled up for several layers. So our device currently has about 4 layers, but we expect it to have anywhere up to 8 or 10. And so that's where the roll-to-roll comes in, is that by having this roll, we're not limited in the size of our device. We can increase it much more easily because all it is adding another 100 micron layer to our device. And the hope is to start with a big roll of clean PDMS sheeting, and then we unroll it in production, we would be able to laser engrave at immediately and re-roll it into devices. And so other things I describe here in the methods is more about how we go creating these devices. But what I want to highlight is that this is a iterative design project, and so what we'll do is we'll create an artificial lung, and we'll test it out using a couple different methods. One of them just being the flow test. So if you see in this image 1, this is actually a successful flow test, where what happens is there's green and red dyed water flowing. If you follow the tubings, they're coming from the left. They're going down and up into the device, and these syringes are actually pushing water, green and red dyed water, into our device. Then the water is flowing through the micro channels. You can slightly see the crisscross kind of pattern there in the next to the reflection in the light, and then they come back out of the device. Notably, these colors are coming out at the same color that they went in as, which tells us that there's no leaking between the two interfaces, which is very crucial, because if the blood were to be leaking to an oxygen channel, then it wouldn't be an effective lung. So that's the first test. Another test we can conduct similarly is a pressure test, to see the pressure drop across the device, and this is the setup that we use. Specifically, it's similar to the setup we saw of the flow test, but these ones also have pressure meters that measure the pressure of the fluid going into the device, as well as the pressure from coming out of the device. Using this, we can take the difference between these two values, as well as use a calibration value and a conversion value to take the millivolt reading into a pressure reading. Lastly, in our methods, we use imaging, both of optical imaging as well as scanning electron microscope imaging, to look at the microchannels in our device, as well as get an understanding of how the fluid acts in our device. So we conduct all these different tests for each of our devices, and based on the results, we go back and modify our design, whether that is changing the pattern that we engrave, if that helps at all, or possibly ways that we make our roll and roll the device. But one in particular that I've been working on is creating a mold for our device. So you can see this here. This was a 3D printed mold that I created. So after we take the rolled device, once that's done, it becomes difficult to add inlet and outlet ports. So I decided to put it in this mold that takes the cylindrical shape and turns it rectangular. So as you can see, there's these rectangular cutouts, but the original device is more of the curved shape that you see in between these rectangular blocks. So what I found is that having this 3D mold serves a couple different purposes. One, it encases the device and helps with any leaks on the sides and keeps it very strong. It also helps us by adding a flat surface to be able to add inlet and outlet ports to the device, rather than having to find a way to connect flat ports to a rounded surface. And lastly, we also connect other parts using this rounded edge as well. It kind of acts as a cap. So this is a very easy way because it's just a 3D printed mold. So it's easy to change the design and easy to make modifications to our artificial lung by changing the mold. And as you can see, these holes up here are how the molding is cast, or the PDMS is cast and poured in and let to set. And as you can see here, these holes are how the PDMS is poured into the vise and allowed to set. So with all this, we do have a current device, which I'll describe where that is right now. So the channels of our device come out to 60 microns deep and 100 microns wide, and I'll show you what I mean by that. If you see here, this is a scanning electron microscope image of our device. Here at 40 times zoom and here at 350 times zoom. And if you look at the measuring scale, this is 500 microns, and then this is at a 50 micron measuring scale. So when looking, this is one of the channels that you see in this image, and the length across is 60 and the depth here is 100 microns, which falls in what we're looking for of microfluidics that is suitable for the blood. Next, our current device uses the mold that I was showing you above, which has been, in my design processing, a big part and effective for me to change and make progress in the design iterations most effectively through the mold. Our current device does have leakage, so we're looking to fix that. We don't have any current data about the current results of the pressure drop across the current device. And currently, based on the mold design, we're able to produce 4 devices just out of 1 roll. Now, moving into some of the discussion about the current device, there are a couple issues. One is that when dealing with microfluidics, size is very important because even dust particles can begin to interfere because of the very small scale and the very small nature of microfluidics. So we do have a cleaning procedure in place, but I believe it may not be enough at this point. So something moving forward would be to either develop better cleaning solutions. Currently, it's to wash our film and our tubing with IPA acetone and DI water. But as you can see here, there's some dust, some hair, and some residue from the 3D or the laser printer that will come on our device. So this could also be that this came onto the device right before it was rolled. So either having more frequent cleaning steps or a more in-depth cleaning step would definitely be needed. I also found that devices that didn't have leaking seem to connect to devices that had had larger spacing between each of the channels, and I can describe this also in image 4. So this spacing right here, when this spacing was large enough, um, the artificial lung was able to withstand the pressure force placed on that channel, and wouldn't rip this barrier in between um, the channels. So hopefully moving forward, there can be tests done to see what is the optimal distance between the channel distance as well as pressure to see what does not cause any ripping or leaking. But this would be something for the future. What I found is, like I was saying, the mold is one of the key components to really be effective in making design iterations. Um, it really is very helpful. So something for the future to continue to be working on. Um, we weren't able to conduct any pressure testing as well as some of the imaging because of the current COVID-19 situation, but we hope to continue those testing, continue those tests, and um, get more imaging of our device. Um, as well as the last concern is the roughness of the channels. So if you look here again, um, it's very jagged and not smooth, but it's more rough, and that could become an issue again when using lung or testing with blood, excuse me, because this could activate the anticoagulant, or excuse me, this could activate coagulation with our device, blood clots in our device, which would be very bad. So something either to clean up these edges, smooth the edges, something like that. Lastly, this roll-to-roll manufacturing has great potential, especially with the pace and trajectory of our progress right now. We see that it's most likely going to be something that's very effective. We also hope to now take this device, if it works, or when we can get it to work, to also be transportable as well. So because of the small nature of the device compared to current devices, we might be able to see it added to possibly backpacks that people can carry with them as new and portable artificial lungs rather than leaving people stuck in hospital beds. Some other notes that about my experience doing this is I got involved in this project through the Year Up program at the University of Michigan, and I've been in this project ever since, and I love it. It's very fun. Some hurdles that came that I never expected were the connectedness of each thing and how there were maybe several different problems at once, but I would have to fix one at a time, kind of using the scientific method to be able to get a proper solution for each one. But that also it made it more fun. Unfortunately, we didn't have time to finish a lot of the things in the project due to the COVID situation, but I would have loved to get pressure tests and find the pressure drop across our device, as well as hopefully get to the point where there's no leaking and then be able to start actual testing with bovine or cow blood to see how our device responds to blood, see how it can oxygenate. So that's something that hopefully in the future I'll get to continue to explore. And my career path in the future will hopefully be to pursue a degree in the medical field. So knowing that these kind of solutions exist out there will help me to continue thinking, knowing that I can find better treatments for my patients. It could also help me in the hope that I also will be doing research in the medical field as well. So this gives me insight into what that research looks like, medical devices or for patients. So thank you again. I hope you enjoyed this presentation, and I hope you're staying safe and healthy at home. I'll zoom out one more time. But other than that, thank you so much.